Welcome, everybody. We're going to be looking at our first module today, or Unit 1, which will be on exponents and radicals. In this topic today, we're going to be talking about factors, multiples, greatest common factors, and lowest common multiples. So let's start by taking a look at our learning targets. In this unit, we're going to be talking about a number of different things. We're going to be looking at um, irrational numbers. We're going to be talking about mixed and entire radicals. We're going to be looking at greatest common factors, lowest common multiples. We're also going to be doing a lot of work with exponent laws. In today's lesson, we're going to be doing kind of a refresher on what a factor and a multiple are, and then we're going to get into prime factorization and then GCF and LCM. So at the end of this lesson today, hopefully you will be able to explain the difference between factors and multiples, identify the factors and multiples of a number, use prime factorization, and we're going to do that with a factor tree. We're also going to look at something called birthday cake. So you're going to use prime factorization to represent a whole number. And then using prime factorization, we are going to look at the greatest common factor of a set of numbers as well as the least common multiple. So let's get into it. All right, so first of all, let's talk about the difference between a factor and a multiple. So when we're talking about a multiple, we're talking about a number that's getting bigger. So I always say when we talk about multiple, we think multiply. So if we want to talk about the multiples of 6, those are all the numbers that 6 goes into. So our multiples of 6 would be 6, and then we can have 6, we can have 12, we can have 18, 24, and so on. So 6 times 1 is 6, 6 times 2 is 12, and so on. So when we have a multiple, that's the result of multiplying a number and an integer. Factors are numbers that are smaller than the number we're talking about. So a factor is all the numbers that divide into that number. So when we're talking about the factors of 6, we're talking about all the numbers that go into 6. So that would be 1, 2, 3, and 6. Now, when we get into talking about factors, when we're factoring in another unit, a lot of times we're going to write these as factor pairs. Sometimes people will ask, how do I know if I've got all my factors? Well, if we write things in factor pairs in order from lowest to greatest, we can often figure out if we've got all of them. So when we're looking at the factors of 6, 1 times 6 gives me 6, so that's a factor pair. And then we have 2 times 3 gives me 6. So if I look at the 2 and the 3, there's no number between the 2 and the 3. That's a whole number that goes into 6. So I know that I've got all of mine. Let's take a look at another example. So if I want to do the factor pairs of 24, well, 1 and 24 go into 24, 2 and 12 go into 24, 3 and 8 go into 24, and 4 and 6 go into 24. And when I look at those, there is a number between 4 and 6, that's 5. 5 doesn't go into 24, so I know that I've got all of my factor pairs. So when we're talking about the factors of 24, they would be 1, 2, 3, 4, 6, 8, 12, and 24. But again, writing them as factor pairs might help make that a little bit easier. All right, some other terms that we would want to talk about because you're going to be hearing them throughout the unit. One is prime number. A prime number is a whole number that has exactly 2 factors, itself and 1. A lot of times you hear that a prime number is only divisible by itself and 1. I want to be very specific about exactly 2 factors because that's going to help us identify some of our special cases. So a prime number has to have exactly 2 factors, itself and 1. So our first prime factor would be 2, and then 3, and then 5, 7, we keep going, 11, 13, and so on. A lot of times when we start writing these out, people want to write a 9 in there because we start to get in the habit of writing our odd numbers, but 9 is divisible by both 1 and 9 and 3, so it's not a prime number. We'll talk about 1 in a little bit. 1 is not a prime number. All right, so if a number is not prime, it's composite. So a whole number that has 3 or more factors um, and a composite number cannot be prime. So some examples here would be 4, 6, 8, 9, 10, and so on. So any number that has 3 or more factors would be a composite number. So if you take a look at those numbers, there are some that are missing, and those are our special cases, and those are 0 and 1. And that's where we're going to go back to that definition of a prime number. A lot of times we just say it's divisible by itself in 1. We want to talk again about that exactly 2 factors. So if we look at why is 1 not a prime number, 1 is not prime because it has only one factor. So in order to be a prime number, it has to have exactly 2 factors. For this one here, 1 only has one factor. So then the question comes up, why is 0 not prime? 0 is not prime because it has infinite factors. Because anything times 0 is 0. And so since 0 has infinite factors, it can't be prime or composite. So numbers can be prime, they can be composite, or they can be neither. And again, the neither would be those 2 cases, 0 and 1. And do be prepared to explain those. Quite often I will ask you, why is 0 not prime? Why is 1 not prime? Just so we keep reiterating that and reinforcing why that is the case. All right, so I do have on the side here in your notes some divisibility rules. I'm not going to get into these in great detail. I'm not going to go through them. These are hopefully things that you have learned throughout elementary and junior high, but I do have them there for reference for you. A lot of times when we're getting into prime factorization, we're trying to decide what numbers go into our bigger numbers. And if you remember some of your divisibility rules, it might make it a little bit easier to start you off or get to that starting point. All right, so we're going to get into prime factorization. With prime factorization, all we're doing is we're writing a number into its prime factors. Think about it like every number has its own DNA. It has its own code, its own secret code. And that secret code is made up of their prime factors. So if I want to break down 48 into the prime factors, I can do that in a couple different ways. One is to use a factor tree. This is probably one that you're most familiar with. So we have 48. We think, what goes into 48? Well, I know that 2 and 24 goes into 48. And I chose 2 because 48 is an even number. So 2 and 24. Well, 2 is a prime number. Can't break it down any further. But 24 is a composite number. It can be broken down further. So we're going to have 2 and 12. And then 12 can break down to 3 and 4. And 3 is a prime number. Can't go any further. 4 can break down to 2 and to 2. And so at the end of each of my branches are these little buds, and those are my prime numbers. So 48 is 2 times 2 times 2 times 2 times 3, and we can verify that with our calculator. Now, another way to do prime factorization is using a method called upside down birthday cake, or I just write it as birthday cake. What we're doing is we're taking the 48, we're dividing by one of our prime numbers. Again, 48 is even, so I'm going to choose to divide by 2. 48 divided by 2 is 24. And now I'm creating my next layer of my cake. So 48 divided by 2 leaves me with 24. 24 is even, so 24 divided by 2 is 12. So I've got another layer of my cake. 12 divided by 12 divided by 2, because that's even. 12 divided by 2 is 6. 6 again is even, divide by 2 is 3. Well, 3 divided by 3 is 1. So I keep creating these layers of my cake until I get down to the little birthday candle at the bottom. And so my prime factorization for 48, again, is 2 times 2 times 2 times 2 times 3. So if I wanted to write that as prime factorization, I can write 48 equals 2 times 2 times 2 times 2 times 3. If I wanted to write it using exponential notation, there's 4 2's, so I could write 2 to the 4th times 3. Generally, you're going to see me write it out in expanded form. All right, so let's take some time to practice here. I want you to figure out the prime factorization for 600 using any method of your choice. So you can use the factor tree, you can use the birthday cake, and then I want you to write your final answer using repeated multiplication and exponential form. So pause the video, try this example on your own, and then come back and check your answer. All right, so let's take a look at what you've come up with. If you've used the factor tree, yours might look similar to what I have in blue. It's really important to note that when we're multiplying, order doesn't matter. So if you had decided to take 600 and divide by 3, and you would have had 3 times 200, your factor tree might look different than mine. However, in the end, your prime factor should be the same. It's the same if you had done birthday cake. So I chose to divide by 2, again, because 2 is going to break it down fastest, and 600 is an even number. Then I had 300. I knew that 3 went into 300. That got me to 100. You might have decided to divide by 2 and then divide by 2 again and had 150 there. So your birthday cake layers might look different, but your prime factors should look the same. They may be in a different order, but they should be the same. So if we're going to write this using repeated multiplication, you don't have to write these in order, but the standard would be to typically write these in numerical order from lowest to highest. So I notice that I have 3 2's. So I'm going to have 2 times 2 times 2, and then I have 1 3, and then 5 times 5. And it's always a good idea when you're doing these to just double check on your calculator. So I'm just going to pull my calculator up here. And if I'm checking, I've got 2 times 2 times 2 times 3 times 5, and that gives me 600. That's going to be really important when we get into GCF and LCM. Often some of our silly mistakes happen right in the beginning because we missed a number, or we overwrote a number, or we doubled up on a number, whatever the case is. Sometimes just silly writing errors can cause problems. So always be diligent about checking your work. Now, if I want to write this using exponential notation, I'm going to notice that I have 2 times 2 times 2. So that's 2 cubed. 2 cubed is 8 times 3, and you could write 3 to the 1 if you wanted, and then 5 squared. Again, if I wanted to check that on my calculator, I could. I can put in 2 cubed. Let's use brackets here. So 2 cubed times 3 times 5 squared. And that also gives me 600. So again, I know that those are both correct. Now, moving on, we're going to talk about greatest common factor and then lowest common multiple. As we go through this, there are lots of ways you can do your prime factorization. Again, you can use factor tree, you can use birthday cake. It's going to be the same when we get into GCF and LCM. There is more than one method. I'm going to use birthday cake. I'm also going to show you a variation of birthday cake that you can use. But again, there's more than one way to do this. Now, when it comes to greatest common factor and least common multiple, there is also the way that we can just write out all our factors or list out all of our multiples until we find the answer. And that is perfectly acceptable. A lot of times it's going to be more efficient to use prime factorization. If on a question you are specifically asked to use prime factorization to determine GCF or LCM, then you have to use the birthday cake or the factor tree method. All right, so let's take a look at greatest common factor. When we're looking at greatest common factor, we're looking at the largest factor that 2 or more numbers have in common. And so we break down that word there, greatest common factor. Let's take a look at what each word means, and it kind of gives us a code as to what we're looking for. Greatest just means biggest. Factor, it's just a number. So we're looking for the biggest number that they have in common. So in other words, we're looking for the biggest same number. So if you're asked for a GCF, you're asked for a greatest common factor, we're just looking for the biggest number that these two have in common. Now, when I'm looking at 81 and 216, I can absolutely figure out all of my factor pairs for 81, all of my factor pairs for 216, and then decide what they have in common. What you'll find is that the bigger the numbers you're given, the longer it takes to list all of those factors. Make sure you have all of those factors. If we're using prime factorization, it just breaks it down a little bit quicker. So we're going to start off with 81. So 81, I'm going to divide that by 3. Again, I didn't divide by 2 because it's an odd number, so my first guess would have been 3. 81 divided by 3 gives me 27. 27 divided by 3 gives me 9. 9 divided by 3 is 3. And then 3 divided by 3 is 1. A common mistake is that we forget to do that last step. We get the 3 and we go, oh, it's 333, and we forget to go to the candle. And sometimes when we're writing things out, we miss that last number. So again, just go back and double check on your calculator that 3 times 3 times 3 times 3 is 81. All right, then we're on to 216. So we break down 216. 216 divided by 2 is 108. Divided by 2 is 54. Divided by 2 is 27. 27 divided by 3 is 9. 9 divided by 3 is 3. And then we've got 3, 3, and a 1. And again, double checking that 2 times 2 times 2 times 3 cubed is 216. Now, we're going to write these numbers out in order, in numerical order, and you're going to notice that I'm putting some gaps in there, and I'm doing that for a reason. So we're going to write out our prime factorization. I'm going to start with 216 just because it's a longer set of factors. So 216 is 2 times 2 times 2 times 3 times 3 times 3, and then 81 is 3 times 3 times 3 times 3. Notice what I'm doing is I'm purposely lining up my common numbers. It'll be easier for figuring out my GCF. So we want to know, what numbers do these have in common? Well, 3, they have 3 in common, they have another 3 in common, and they have another 3 in common. So my GCF is going to be 3 times 3 times 3, which is 27. All right. Now, let's take a look at example number 2. Again, I want you to write out your prime factorization, write out your numbers, and then come back and check to see how you did. Okay, so now let's take a look at your prime factorization. So I have the birthday cake parts up here. We've got, for 120, we've got 2 times 2 times 2 times 3 times 5. 960, we have 6 2's and then a 3 and a 5. And then for 1400, we have 2 cubed times 5 squared times 7. When we're doing GCF, again, we're looking for what all three numbers have in common. Greatest is the biggest, factor is the number, and we want the biggest number that's the same. So for every grouping, we pull out the number one time. So when there's three numbers, we're looking for triplets. When there's two numbers, we're looking for twins. And so we're looking for a group of 3 2's. We've got another group of 3 2's and another group of 3 2's. And then if we go down the line, we also have a group of 5's. So our GCF for this number would be 2 times 2 times 2 times 5. So 2 cubed is 8. 8 times 5 is 40. So the GCF for those three numbers is 40. Now, before we move on to least common multiple, I want to show you an alternative way using a variation of upside down birthday cake that you can also do GCF. So I'm just going to erase this here, and then we're going to go through the alternative method. All right, so let's take a look at the alternative method. So what we're going to do is we're going to have 81 and 216, and so I'm going to write them side by side. And what we're doing when we do our upside down birthday cake this time is we're asking ourselves, what's a number that goes into both 81 and 216? Well, 81's not even, so I'm not going to start with a 2, but if I check, both of these are divisible by 3. So 81 divided by 3 is 27, and 216 divided by 3 is 72. Again, I'm asking myself, what's a number that goes into both 27 and 72? Again, 3 goes in. 27 divided by 3 is 9, and 72 divided by 3 is 24. Once again, we can divide out a 3. 9 divided by 3 is 3. 24 divided by 3 is 8. Now when I'm looking at these two numbers, 3 and 8, there is no number that can go into both 3 and 8 other than 1. So then we can stop there. On the side here, what these have in common is my GCF. So the GCF for 81 and 216 is 3 times 3 times 3 is 27. Using that alternate method, I'd like you guys to try doing the GCF for 120, 960, and 1400. So again, pause your video, try the question, and then come back and check your work. All right, so again, check out your birthday cake. The numbers may look different if you had started dividing by 5 before you divided by 2. I have a tendency to go from my lowest to my highest because it breaks down the numbers faster. But no matter what, down the side, you should have 3 2's and a 5. So my GCF would be 2 times 2 times 2 times 5. If you notice at the bottom, I've got a 3, a 24, and a 35. There's no number that goes into any of those, so that's where I stop. I can't go any further. So my GCF, again, is 2 cubed times 5, or 8 times 5, which is 40. All right, moving along to least common multiple. Just like before, each of those three words has meaning, and they're going to tell us what we're looking for. So least would mean the smallest. Multiple, just like factor, is a number. So we want the smallest number that's in common, or the smallest same number. So when we're looking for greatest common factor, we're looking for the biggest number that's the same. When we're looking for least common multiple, we're looking for the smallest number that's the same. And the process is exactly the same in the beginning. We start off by using birthday cake. We're going to figure out our prime factors, write out our list, and then go from there. So for LCM of 6 and 8, 6 and 8, we can break that down. 6 divided by 2 is 3. 3 divided by 3 is 1. 8 divided by 2 is 4. 4 divided by 2 is 2. 2 divided by 2 is 1. These are fairly small lists to write out, so we'll write out 6 and 8. 8 is 2 times 2 times 2. And again, with the 6, I'm lining up my prime numbers or my common numbers. So I've got 2 times 3. Now, when we're doing LCM, the first thing we do is find out what they have in common. And so in this case, that's a 2. Anything else is part of that least common multiple. So my LCM is going to be 2. Again, remember, every circle we pull out the number 1 time. So there's going to be a 2. And then all of my singles. So we've got 2 times 2 times 2 times 3. And so 2 times 2 times 2 is 8. 8 times 3 is 24. So my lowest common multiple is 24. Now remember I said you could, if you wanted to, just list out all of your multiples of 6 and list all your multiples of 8. These are small numbers, so this might be a good way to check your work. So I know that I think about my multiples of 6. I've got 6, 12, 18, 24, 30, 36, and so on. And I could just keep writing them until they line up. 8, I've got 8, 16, 24, 8 times 4 is 32, and so on. But I've already come across ones that are in common. And notice that my LCM is 24. Again, with small numbers like 6 and 8, or maybe even 10 and 12, we're not going to have really long lists. So you are absolutely welcome to write out your list of multiples and then find out what they have in common. No different than if we were looking for our greatest common factor. List all of your factors of the numbers and then look for the biggest one that they have in common. It becomes a challenge when I have 3 or 4 numbers or I have really big numbers. This becomes a very inefficient method, but it's absolutely a great way to check your work. All right, so let's take a look at the 3 numbers here. Now this one I'm going to talk you through because it is slightly different when we're looking at more than 2 numbers. So I've got 20. 20 divided by 2 is 10. 10 divided by 2 is 5. 5 divided by 5 is 1. And then we've got 36. Divided by 2 is 18. Divided by 2 is 9. Divided by 3, 3, 3, and 1. Common mistake as we're doing these is to divide by numbers on the side that are not prime. A lot of times we go, oh, I know that 36 divided by 6 is 6, and we divide by 6. 6 is not a prime number. So we always have to make sure that what's on the side here are prime numbers. And again, using your calculator to double check that 2 times 2, that's 4. 4 times 5 is 20. Good. 2 times 2 is 4. 4 times 3 is 12. 12 times 3 is 36. We're good. Just always double checking those numbers so that you avoid those mistakes at the end because of a silly mistake in the beginning. All right, so 38 divided by 2. 38 divided by 2 is 19. 19 is a prime number, so 19 divided by 19 is 1. So that had a very short list of factors. All right, again, we're going to write out our prime factors. So I start with 36. 2 times 2 times 3 times 3. 38 is 2 times 19, which is way over here. And then 20 is 2 times 2 times 5. Now, again, this is really important that you're as organized as possible. This is one of the reasons I like birthday cake a little bit better than factor tree. It keeps my information a little bit more organized. I find factor trees can be a little more scattered. But again, both methods are perfectly acceptable as long as you get to the same answer in the end. Now, when we're looking for our LCM, again, we start off by looking at what they have in common. In this case, we have 3 numbers. So that means we're looking for triplets, then we're looking for twins, and then we're looking for the singles. I often start breaking into a Beyonce song here, looking for our triples, our doubles, and then all the single ladies, da, 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 da. All right, so we're going to look for our triplets. There's a group of 2. There are my pairs, a pair of 2, and then all the rest are all the singles. So we're going to circle our singles. And my LCM is going to be 2. Remember, for every circle, we pull out the number once. We've got 2 times 2, and then all the singles. All right, so again, we've got our triples, our doubles, all the single 80s, all the single 80s, da 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 da. And if we multiply that out, we have 3,420. Can you imagine if you had to write out all of your multiples of 20, 36, and 38 and just keep going till you got to 3,420? Doesn't sound like a lot of fun, but our prime factorization method will help break that down quite quickly. So let's take a look at the alternative method for finding LCM. This one's a little bit of a twist or a little bit tricky as we go through. There are videos on YouTube that will show examples like say 6 and 8, but when you get into more complex examples like especially when you have three numbers or more than three numbers, there is a little bit of a twist that you have to be aware of. And so if you just watch those videos that are showing the 6 and the 8, you might end up making a little mistake as you get into more complex numbers. All right, I also noticed here that it says determine LCM here and it says determine GCF here, but we are doing LCM, so I'm just going to change that so that says LCM. All right, so our first example here, we've got 6 and 8, so we're going to write out the 6 and the 8, and both of those numbers are divisible by 2. So 6 divided by 2 is 3. 8 divided by 2 is 4. Now there is nothing that goes into the 3 and the 4. So in theory, we know that the LCM, from having done this example before, we know that the LCM is 2 times 3 times 4, which is 24. So we could just say that's our answer. And that would be great, except that method will not work when we get further into the bigger examples. So I'm going to just show you the method straight off. So we have our GCF. Our GCF is 2. That's what they have in common. Now we look at the 3 and the 4. 3 is a prime number. It can't be broken down any further. So I'm just going to bring it down. So I'm not actually dividing by anything. It's just that 3 divided by 1 is 3. 4 is not prime. It can still be broken down. So 4 divided by 2 is 2. And now I have everything broken down into my primes. There's my LCM. So my LCM is all of those numbers being multiplied. So my LCM is 2 times 2 times 2 times 3, which is 24. And again, you could say, but wait, 2 times 3 times 4 gave me 24. Aren't I good? I'll show you how that works with our next example. All right, so in our next example here, we have 20, we have 36, and we have 38. And again, if you remember from your notes, when we just did this example before, the LCM of this number is 3420. So we're going to start off with our common factor. So all of these numbers are divisible by 2. 20 divided by 2 is 10. 36 divided by 2 is 18. And 38 divided by 2 is 19. And you can say, well, wait, there's nothing that goes into 10, 18, and 19, so that must be my answer. If you were to multiply 2 times 10 times 18 times 19, you're actually going to get, let's see, 2 times 10 times 18 times 19 is 6,840, which we know is not our answer. And so that's why we have to keep going further. The 19 can't be broken down. So we do know that our GCF is 2. So if I was being asked for GCF, that would be my answer. My GCF is 2. LCM, we go further until everything is broken into its primes. 19 is prime, can't be broken down any further. But 10 and 18 are both divisible by 2. So I'm going to divide by 2. 10 divided by 2 is 5. 18 divided by 2 is 9. 19 is prime, 5 is prime. They can't go any further, but 9 can still be broken down. So I'm just going to bring down the 5 and bring down the 19 because I can't go any further with those. 9 divided by 3 is 3. Now I have everything broken into primes. And if on my calculator I wanted to check 2 times 2 times 3 times 5 times 3 times 19 gives me 3,420, which I know from doing this example a different way is my answer. So we have 2 squared times 3 squared times 5 times 19 gives me 3,420. So again, this is an alternative method. Some people like using this again because it's a little more organized, uses up a little less space on your paper. Some people don't always like writing out the numbers the way I was doing before with the gaps. So again, just another format that you can use. As well, the option is to write out all of your multiples of 20, all your multiples of 36, and then 38 until you get to 3,420, but sounds like a lot of work to me. Now last, let's take a look at word problems. When it comes to word problems, the most challenging piece is often figuring out, is it a GCF problem? Is it an LCM problem? Where do I go with it? So I'm going to go through some keywords that you might look for when you're solving a word problem related to GCF and LCM. It's also important to note that sometimes in your assignment, it's pretty easy to figure out which it is because maybe you've just done a whole bunch of questions on GCF and then there's a word problem. Oh, it's a GCF problem. It's when everything comes together that we really have to pay attention to those keywords. So when we're talking about a GCF problem, again, remember GCF is greatest common factor. So biggest number that's the same. That means we're often looking for something that we started with big numbers and we're breaking them down. Because again, when we're factoring something, we're breaking it down. So often we're dealing with things where we are grouping items. Like maybe I've got a big banquet I'm planning, I've got so many athletes, and I want to have everybody grouped with so many people at a table, and I have a certain number of tables. How many can I put at each table? That might be a GCF type question. We might be asked to split or divide equally, or divide with no leftovers. We might be sharing, and then like I said, something with no leftovers. So we have a big number and we're breaking it down. So often that's what I'm thinking about. I've got a big number and I want to break it down. And you can always see those keywords too for greatest or largest. They might say, what is the greatest number of people that we can put together, or what's the largest amount of candies we can group together, that type of thing. When we're getting into LCM, often we're talking about repetition. I will often tell my students that we're looking at starting at a certain place and then moving forward. So maybe I have a bell schedule. We ring the bell at this time, and every 15 minutes this bell rings, and then every 20 minutes this bell rings. If I ring them at the same time now, how long until they ring together again? So there's sort of a repeated cycle there. So cycle might be another keyword. Or maybe I'm mowing the lawn and I mow the lawn on this day and my neighbor mows the lawn on this day, and I mow my lawn every, I don't know, 5 days, and my neighbor mows the lawn every 7 days. If we mow the lawn on Sunday, how many days until we mow the lawn on the same day again? So that would be an LCM type question. So I was just saying that, so we happen, things that happen at the same time again. And then, like I was saying before, maybe it's you start at the same time and then you're moving forward. So GCF questions, we have a big group or a big number, and we're breaking it down into smaller groups. Here, we have often a repeated cycle. We have something that happens at a certain time, and then they're happening at different times. We want to know when are they happening at the same time again. And just like GCF, you'll also just see that basic keyword of smallest or least. Okay, so those words will often be quite explicit right in there. So let's jump into it. Let's take a look at these word problems and let's decide which type of word problem are they. So it says Jeremy has two pieces of lumber. One is 90 inches and the other is 72 inches. He wants to cut both pieces of wood into smaller pieces so that all the pieces are the same length. So there's a key word right there. We're looking at something that's being the same length. If he wants the pieces to be as long as possible, and doesn't want to have any lumber left over, so no leftovers, how long should each piece be? And then the question is, how many total pieces of lumber will he have? So again, as we're looking at these keywords, we've got a bigger piece of lumber that we're cutting down into smaller pieces. We want everything to be equal amounts, so divided equally, the same length, and we want no leftovers. This is a GCF question, and so we're looking for the GCF of 90 and 72. So pause the video, find your GCF for 90 and 72, and then come on back. All right, so I used the alternative method for this particular example, and I have that the GCF of 90 and 72 is 18. So that means that each piece of lumber, once they're cut down, is going to be 18 inches in length. So that's the answer to my first question. How long should each piece be? It will be 18 inches. The next question is, how many pieces of lumber will I have? Well, if I take 90 inches and I divide by 18 inches, that's going to give me 5 pieces of lumber. And if I have 72 inches and I divide by 18, that's going to give me 4 pieces of lumber. So the total together, we're going to have 9 pieces of lumber. Let's take a look at example number 8. Kara and Eli are in different math classes at EBHS. Kara's teacher always gives exams with 30 questions on them, but Eli's teacher gives more frequent exams, but they only have 25 questions. Eli's teacher also assigns 3 projects per semester. Even though the two classes have to take a different number of exams, their teachers have told them that both classes will get the same total number of exam questions each semester. Maybe not the most realistic example. I don't know many of us that count exactly how many questions we do and compare with another teacher, but for the purpose of this example, we're going to use this. What is the minimum number of exam questions that Kara or Eli can expect to get in a semester? So again, let's look for some keywords here. We have that they're in different math classes. One is getting 30 questions, one is getting 25 questions, and then there's that distractor information in there. It really doesn't matter that Eli's teacher gives 3 projects per semester because we're not talking about projects, we're talking about the test questions. The two classes have different number of exams, but they're told that they're going to get the same total number of exam questions each semester. So take a look at the top and decide, are we looking for GCF or are we looking for LCM? All right, so we are looking for LCM because it says the minimum number of exam questions. That's the least number. So we're looking for the smallest number. So we're looking for LCM. So again, I'm going to have you pause the video and find the LCM of 30 and 25. All right, so I've used our original method here for LCM. I've got that 30 is 2 times 3 times 5, and 25 is 5 times 5. If I'm looking for my LCM, again, I look for what's in common first. There's 2 numbers, so I'm looking for the doubles, and then I'm looking for all my singles. So my LCM is going to be 2 times 3 times 5, which is 150. So given this example, the two students will write a minimum of 150 exam questions in the semester. One more. So let's take a look at example number 9. Example number 9 says a store has a package of 21 erasers, a package of 30 pencils, and a case of 36 binders on clearance. Mrs. Krause wants to buy enough pencils, erasers, and binders to create identical sets of school supplies for each student in her tag class. If there are 18 students in my tag, what are the least number of packages or cases of binders, pencils, and erasers that I need to buy in order to create identical sets with no leftovers? And then the next part of that question is how many pencils, erasers, and binders will each student receive? So I want you to take a minute, pause the video, look for some of your key words, and decide, is this a GCF or is this an LCM question? This is actually a bit of a special case. This is kind of a little bit of both. So we're looking for some keywords in here. We have the 21 erasers, we've got the 30 pencils, and we've got the 36 binders. So that's what's coming in each case. I want to buy enough to create identical sets. So that's going to tell me we're dealing with GCF. But then we also see the least number of packages. So this is actually a question that's going to combine both GCF and LCM. So let's take a look at how we break this down. First of all, we're going to look for our GCF. So I have 21, I have 30, I have 36. And so again, I'm going to use that alternative method for this one. All of these are divisible by 3. 21 divided by 3 is 7, 30 divided by 3 is 10, and 36 divided by 3 is 12. Nothing goes into 7, 12, and 10, so my GCF is 3. But we have 18 students in Mrs. Krause's class, and so 3 sets isn't going to be enough. So this would have said that with 21, 30, and 36, we can make 3 identical sets, but I have 18 students. And so 3 times 6 is 18 students. Now, what I need to do is figure out how many packages of each am I going to need. So that means I'm going to have to find the LCM of 18 and 21. I'm going to have to find the LCM of 18 and 30. And I have to find the LCM of 18 and 36 because I want to see what is the amount that I'm going to need. Now, just to save some time here, my LCM for 18 and 21 would be 126. My LCM for 18 and 30 would be 90. And my LCM for 18 and 36 will be 36. And so I know that I'm going to need 126 erasers. Well, if I take 126 and I divide by 21 erasers, 126 divided by 21. That means I'm going to need 6 cases of erasers. And 90 divided by 30. 90 divided by 30 is 3. That means I'm going to need 3 cases of pencils. And 36 divided by 36 is 1. So I'm going to need one case of binders. Now that answers the first part. How many of each package will I need to buy? I'm going to need 6 cases of erasers. I'm going to need 3 cases of pencils, and I'm going to need 1 case of binders. The next part to that is how many pencils, erasers, and binders will each student receive? Well, if there's 126 erasers and I divide by the 18 students, 126 divided by 18 is going to be 7. If I have 90 pencils and I divide by the 18 students, 90 divided by 18 is going to be 5 pencils each. And the last part, I only bought 1 case. That means I've got 36 binders divided by the 18 students. That's going to be 2 binders per person. So 7 erasers per person, 5 pencils per person, and 2 binders per person. So you quite often will not expect to see a question like this. This is just an example of one where we can actually put LCM and GCF together. And again, you're looking for those keywords. We had these bigger packages of erasers, pencils, and binders. We wanted to break them down into identical sets. That's the GCF part. But then I wanted to find the least number of packages. So knowing how many students I had to figure out my LCM for the number of students and the number of items in each package. And then from there, I was able to go and figure out how many pencils, erasers, and binders each student would receive. There is an extra piece at the end here if you want to choose to do it as an extension. I will work through the example here and post it at the end, but this is just an activity that you can use to identify prime and composite numbers. Again, pause the video, try it for yourself, and then come back and check your answer. Thanks a lot, guys. See you next time. If you took the time to try this bonus activity, the one piece that needed to be clarified in the directions is that when you're crossing out the multiples of 3, the multiples of 5, the multiples of 7, don't include the 3, 5, and 7 because those are prime. If you've done everything correctly, your chart will look similar to this. And then if you sift the sieve correctly, these would be your answers: zigzag, bookcases, easygoing, headphones, and tuxedo. So that's everything for today. Hopefully you have a better understanding of LCM, GCF, factors, multiples, and the different methods that you can use. See you next time.